They have really bright lights.
Yeah, I can't even tell how many people are in the audience because.
All right, so I think we're going to go ahead and get started. I think we have something a little bit different for you today, right? The topic here is geoengineering to mitigate climate change. Is there a role for aerospace? And I'm Marty Bradley. I represent the Green Engineering Program Committee, which I'm going to tell you a little bit about as an intro to this session. Within the AIAA, we have a topic called green engineering. And in our program committee, we cover topics that are listed here, things like energy conversion efficiencies, and you see a picture of a gas turbine engine. Biofuels are something we're interested in. Climate monitoring is on our list. Improved operations, more efficient operations of aircraft. Recycling, advanced materials, renewable energy, things that involve improving the efficiency of aircraft. And we do a lot of work supporting conferences. We support sessions like this. They're more of a discussion. We support technical sessions in these areas of green engineering. And the charter of the Green Engineering Program Committee is to promote a holistic systems approach to improved energy efficiency, sustainability, renewable energy, and cradle-to-grave design practices. The Green Engineering Program Committee is the focal point within the AIAA for green aerospace-related technologies programs. And we work across the other committees. A lot of committees work on different technologies that support the area of green aviation, green engineering, and green energy. So one of our goals is to work and coordinate across all the various committees involved in these kinds of technologies. Okay, I want to promote, we are having a meeting of the Green Engineering Program Committee. Here's the paid commercial message here. It's later today. It's 5:30 in the Mustang 5 room. So this is where we'll have a presentation on a green energy topic, as well as doing planning for the next year of our committee. So if you're interested in getting more involved in an AIAA committee, and if you're interested in this one, then come visit us. We have a social media presence. We have a Facebook page. We have a website, Twitter, email. So anyway, we try to have as much outreach as we can. We're always looking for new members. The panel today is pretty interesting. A little bit of history. 2 years ago in Florida, we had a panel, similar format, called Climate Change and National Security. And we had a whole array of good speakers, and we had a good and engaged audience. And two things I remember from that panel that I wrote down as I was attending, it was a quote, "Climate change is too important to be left to the environmentalists." So we're engineers, we want to do something, so we're interested. We don't want to just leave it to the environmentalists. Geoengineering was mentioned a couple of times in that panel, but when it was mentioned as a dangerous option due to complexity and uncertainty involved in doing something in the area of geoengineering. And it was quoted, "the iron law of unintended consequences." So the possibility of trying to do something to mitigate climate change and actually making the situation worse in one or more ways. So that's the kind of what we were concerned about. My thought, though, as an engineer, was we need to consider how aerospace may be able to help with this. So we want to have a panel to talk about that by bringing in people that are experts in the area of geoengineering and have been working this for some time, because most of us in our day-to-day lives don't really touch on this very much. So the panel is a discussion of possible ways to reduce climate change with an emphasis on, but not exclusively related to, the aerospace aspects of it. Okay. The description of this panel, geoengineering is using technology to counter the effects of climate change, and it is a controversial topic. Some think the idea is counterproductive as it diverts the attention away from resources that might be better spent reducing our greenhouse gas emissions instead. So I think we'll talk about that. Some other people, though, are concerned this may be the only way to mitigate runaway climate change if we can't cut back on our greenhouse gas emissions. Or it may just buy us time so we can develop some of the more environmentally friendly low-carbon energy sources. So the questions that we want to talk about today are, should we be studying how to use high-altitude systems that we know a lot about, but use them for observation that would help generate data and observe the effects of climate change? Should we be as brave as to start altering the atmospheric chemistry in some way to try to change the situation? There are ideas on deploying reflectors or scattering objects using space systems that have been out there, and we'll talk some about that. And then talk about some of the other possible solutions that have geoengineering kinds of applications. Okay, we have 3 speakers today. We had 4 scheduled, and Will Burns, unfortunately, had a family emergency and had to go home this morning. So we have 3 people, and we're going to change the order a little bit, and Doug McMartin is going to go twice. I'm going to give a little intro of each person, and then we'll start with the discussion and the presentations. So Doug McMartin first. Raise your hand, Doug, so you can see who you are. He's a research professor, the Department of Computing and Mathematical Science at California Institute of Technology, and a senior research associate, Department of Mechanical and Aerospace Engineering at Cornell University. Okay, next we have Martin Bunzel. Raise your hand. So he's a professor emeritus of philosophy at Rutgers University, where he specialized in the philosophy of science. He's the author of Uncertainty and the Philosophy of Climate Change. And let's see, he has a nice website. It's easy to remember, www.bnzl.org, if you want to look him up. And then our other speaker is Tim Langenkamp, who's a partner at the law firm of Sidney and Austin in Houston. And he'll be talking. So first up, though, is going to be, after me, will be Doug McMartin, who'll work through his slides.
Great. You want to pass me? I'll just sit. So I'm going to try and channel Will just a little bit at the beginning here, since he couldn't make it. So I'm Doug McMartin, and I actually am an aerospace engineer. I used to do control of vibrations and noise control and flow control and things like that, and gradually got more involved in climate science. And I'm going to say a little bit at the very beginning here about geoengineering, and then at the very end, I will wrap up with some of these other topics, diving down a little bit more deeply into what the role is for aerospace. The washed out picture in the background here that you can barely see is the eruption of Mount Pinatubo in 1991. The main eruption, this is actually from an earlier part, the main eruption put about, I think it was 20 megatons of sulfate aerosols into the stratosphere. And that cooled the planet by about 0.5 degree the following year, just by reflecting some of the sunlight away from the planet. So that's basically an existence proof for at least the idea, not saying it's a good idea, that you could, if you wanted to, intentionally cool the planet. Let me just describe the overall context here a little bit. The general, if you think about business as usual, let's go burn all the fossil fuels we've got. Climate impacts gradually increase with time until eventually we run out of fossil fuels. That produces a extremely hot planet. And the baseline approach is let's cut our carbon emissions as aggressively as possible. There are two ideas that fall under the broad rubric of geoengineering are things like the solar geoengineering that I just mentioned, so things like putting aerosols into the stratosphere that would cool the planet, and this other idea of sucking carbon out of the atmosphere. You can think of CO2 removal, that's things like planting trees, potentially direct air capture, so if you can chemically capture the carbon dioxide and then store it underground in deep reservoirs. The biggest challenge with the CO2 removal is it's really hard to scale up to a level that would reduce the temperatures dramatically. And so this is sort of a long-term issue and potentially an expensive issue. One of the interesting things about solar geoengineering is that it's very quick. And it's probably very cheap. Cheap in the grand scale of things, on the order of billions of dollars to implement. All you have to do is basically fly airplanes up into the stratosphere and dump a pile of crap up there, and you'll cool the planet. A few other observations for context here. The Paris Agreement last year set as a target for avoiding dangerous climate change a global mean temperature of 1.5 to 2 degrees Celsius. We don't actually know what the threshold for dangerous climate change is, but the other thing the Paris Agreement did is it put targets down for carbon emission reductions. And if you add all of those commitments together, you get to something like a 3-degree warming, maybe a little bit more than a 3-degree warming, assuming that we actually follow all of those commitments to cut carbon emissions. So there's this enormous gap between what we know how to do, or at least what we're committed to do in terms of cutting carbon emissions, and the amount of warming that we think is potentially dangerous from climate change. And so that at least raises the question of maybe there's a role for some of these solar geoengineering technologies. And I would simply say that's a plausibility argument. That's basically context for it. So it is not at all obvious whether following this blue path is in fact less risky than following that green path. It's clearly you can make the planet colder, but if you push in one direction with increasing greenhouse gases and then you try to push backwards in a different direction by cooling the planet, you don't actually recover the same climate you would otherwise have had. So I'll talk a little bit more about that at the end in terms of some of the modeling results as well.
Chart, is that 100 years, 200 years, 50 years?
That's an excellent question. We're actually I have a project right now trying to put some better numbers on that. This start date here, I'll get into again towards the end. That is probably, at least 20 years away, I hope. In part because we don't know enough right now to even start to think about that. If you think that the pathway we're on for cutting carbon emissions will put us to about a 3-degree warming, and 1.5 degrees is the level we'd really rather not exceed, then that arrow is about 1.5 degrees, and this arrow is probably several centuries. That is the fastest that you can conceivably suck CO2 out of the atmosphere. This slope is actually really not that steep. So if you let yourself get to 3 degrees, you're probably committing to something like 3 centuries of warming. I'm going to go, I want to say a few more words about geoengineering, I guess whether you call it solar radiation management or solar geoengineering. What it is not is a substitute for mitigation. This is not a get out of jail free card that says, oh great, now we can just burn all the carbon and we've just got this magic technical solution. This doesn't work for all sorts of reasons. One of them is the fact that you then are committed to doing it for thousands of years. Another is that we probably don't even know how to cool the planet by as much as you would need to. And the third is that even if we did know how to do that, if you push the system that hard in one direction and then try to push it back really, really hard in another direction, you're going to screw something up. So this is not a good idea. Is there a back arrow on this or only a forward arrow?
There's a small red arrow.
There's only progress.
It might work.
Okay, there we are. Whoop, I didn't mean to go back there. So one other thing I wanted to say about this, I mentioned the stratospheric aerosols. There are a couple of other ideas on the table. One would be brightening marine clouds, so spray salt water into low marine clouds. That makes them brighter, but is interacting with climate physics in the most uncertain way there is. We do not understand cloud aerosol interactions very well. One of the other things that you could in principle do, and I'll come back to this at the very end, is put something out in space that would reflect some sunlight. The challenge with that is that it's insanely expensive. And so most of the time when people are thinking about solar geoengineering, they're mostly thinking about stratospheric aerosols. So I think at that point, maybe I'll pass it over to you to say more about some of the issues.
Okay.
Okay.
Did you want the...
No.
Okay.
Thank you. Well, thank you for inviting me, Marty. I'm a philosopher by training, and so I'm a professional skeptic. You know, I'm not sure. I might be a brain in a vat, and you might be a figment of my imagination. But more to the point, I'm not sure if carbon output by human beings is causing climate change. By the same token, I'm not sure if smoking causes cancer. But I gave up smoking at the age of 20, and the reason I gave up smoking at the age of 20 is that it seemed to me a plausible decision under uncertainty to not smoke, given the probability or even the possibility that smoking causes cancer. Now, I say this as a preliminary remark, and I make it every time I speak about any topic related to climate change, because I think it's a fool's errand to think that someone needs to be or even can be convinced that it is, quote, a fact, an incontrovertible fact, that human beings are causing climate change in order to get any debate about climate change or geoengineering going. The plausible, the rational, the sensible way to proceed is to say, following Pascal's wager, that we don't have as much to lose by being cautious in this regard as we have to lose by being cavalier. By the way, Pascal's wager is a bad wager about God's existence, because if there is a God, he might be very angry with someone who opportunistically declares a belief in God because it seems a sensible thing to do. But in every other area, like this area, following Pascal's wager, assuming that climate change is caused by human beings, even if it turns out not to be, is a sensible course of action. Well, I'm going to talk to you a little bit about what I think the current situation is with regard to energy consumption and energy output, and why I think that some kind of negative emissions program is inevitably going to be in our future if we want to proceed cautiously. At the same time, I'm going to talk to you about why I think solar radiation management, at least by putting sulfur particulate matter into the atmosphere, is a plausible stopgap measure, but it's a plausible stopgap measure that faces insurmountable problems with regard to a number of different areas. And by the time we settle the issue or come to a circumstance in which we think it might be necessary, we will be long beyond the area in which we ought to become serious about the long-term program of carbon dioxide removal. So let's talk about the present reality, and let's talk about the Paris Agreement for a minute, following up on Doug's remarks. Doug is, of course, correct that the Paris Agreement, even if it's implemented, is woefully inadequate in terms of levels of restraint of carbon dioxide in order to actually limit to the goal of 1.5 or 2 degrees Celsius. We have to ask, though, what the implications are if the Paris Agreement is not followed. And with the new administration in the United States, we face a serious risk that that agreement may not be followed. That agreement is a non-binding agreement between parties that depends on all of the parties showing enough mutual goodwill for the process of mutual trust to be built. And the assumption was always, among professionals, that the parties would come to realize in about 10 years that their agreement was totally inadequate, but have built enough mutual trust to begin to ramp up the mutual obligations that they would take upon each other going forward. And so the big question going forward now, as of January 20th, is if the United States abrogates the Paris Agreement, what will that mean for Chinese conformity to the agreement, and what will it mean for Indian conformity to the agreement? That's one reason to think geoengineering lies in our future, even more so now than it did had the Democrats won the election. But there's another reason to think that geoengineering lies in our future, even if the Paris Agreement was implemented as originally conceived, even if the parties came together and ramped up their obligations on each other of 5 or 10 years. And that is that if we follow the International Energy Agency projections, energy is going to rise by 40% within the next 30 years, and 75% of that energy increase is going to be due to third world energy demand. Looking at the current level of renewable energy and nuclear energy, and looking plausibly, as engineers do, as opposed to environmentalists, as the realistic rate in which a new infrastructure can be built out, relying on historians who have looked at energy transitions in the last century, serious people making projections think it is totally implausible to think that the rise in energy demand over the rest of this century can be significantly satisfied by renewable energy. In fact, if you look at IEA projections towards the middle of this century, as energy rises relative to renewable energy, we still at about 75% carbon fossil fuel energy as the century moves on to satisfy energy demand. Well, you might say, if I ruled the world, I would simply limit energy growth and let people live with the consequences and let energy grow only when the renewable and nuclear portfolio is built up. There is an interesting price to be paid for that level of totalitarian restraint, even if you can impose it. Some of my colleagues and I have been researching the relationship between population growth, economic growth, and energy demand. And we think there is a reliable relationship between rising economic wealth and declining fertility, and a reliable connection between rising economic growth and rising energy demand. The United Nations projects that population will stabilize at 9 billion to 10 billion, up from the current 7 billion by the end of the century. But at current rates of fertility, the population will in fact be 15 billion by the end of the century. The United Nations is assuming a consistent level of economic growth for the rest of this century, which will be associated, at least historically, with a decline in fertility. Limit energy, you limit economic growth. Limit economic growth, we think fertility continues to grow at the present rate, or it consists of this present rate, and you end up with 15 billion people. Look forward to energy demand for those 15 billion people in order to sustain economic growth so their fertility decline, and the problem is much larger than it is now. So I think it is inevitable that geoengineering has to be part of the portfolio of the response. And the question is, what are the prospects for solar radiation management in the short term, as Doug has laid out, as opposed to air capture in the long term? And we all know that air capture is the only long-term solution. So I want to mention 3 hurdles that solar radiation management, at least if it's sulfur dioxide particulate matter inserted into the stratosphere, has to overcome if it is to be a plausible program. And they are in order: the question of our ignorance of physics, the question of the logistics of scale, and the question of unknown side effects. The first 2, I think, are relatively easy to answer. The third I want to suggest to you is in fact very difficult to answer. Well, with regard to ignorance of the physics, we've done almost no experimentation on the behavior of aerosols in insertion in the stratosphere, their behavior when they're put in the certain level of density, their life cycle in the atmosphere. And these, however, are relatively easy to do for a very small amount of money. There have been very few serious studies of the logistics to put in place aerosol insertion at the scale that would be necessary to have the desired effect, but that too is relatively easy to do, and whatever the level, we're not talking about significant portions of world GDP to do this, although the logistics, at least on a National Science Academy panel that I was on, were mind-boggling and akin to some of the logistics of World War II mobilizations of munitions in order to do it at the scale required. But I'm open that this is easy to answer. What is difficult to answer is the question of unknown effects. It's not just the issue of unintended consequences that Marty raised as sort of from an argument of total ignorance, as it were. It's rather this. We have some current modeling studies of climate that suggests that sulfur dioxide insertion at the scale required in order to have a significant effect, which is less than Mount Pinatubo if it's done on a repeated basis, on an annual basis, may have local effects in terms of precipitation and temperature that are the adverse of what one would hope, and it may have it in significant areas of the world, in sub-Saharan Africa, in India, and in the Amazonian regions. And that this could affect billions of people in terms of food supply and agricultural productivity. Now, what is interesting about this issue is the question of whether or not one could do studies to try and clearly identify the nature and risk associated with that level of insertion for those kinds of effects. And what I think is interesting about solar radiation management, and relatively rare in the case of, as a case for science in general, is that it's extremely difficult to implement what I call a modular research program. Think about how you research something new where you don't know the risks that are involved. You do a laboratory model. You then do a limited field model, and from that field model, you gradually expand. Think about it with regard to a medical drug to be used on humans. You start with some in vitro studies, you then do some animal studies, you then do studies on humans that are dying in any case, and then you slowly ramp up the dosage and increase the number of people that are getting it. At each stage in this study, you have a way of calibrating for unintended consequences or unknown side effects and conducting a risk analysis. Well, why can't you do that with solar radiation management? Well, think about it. The problem is one of trying to insert sulfur dioxide into the atmosphere as a whole. You can't build a model of the whole atmosphere in a laboratory. You can't build a model of a whole atmosphere curtained off from the rest of the atmosphere to do this kind of study. The only thing you can do is insertion into the atmosphere as a whole. What you can do if you assume a linear relationship is start with a low dosage, look for effectiveness, and more importantly, look for untoward effects, and build the dosage up over time. Question then becomes, given the dosage that you start with, how long does it take to collect data to differentiate noise from signal? If you look at recent studies, theoretical studies that have been done on this, they suggest that you need at least 20 years in order to do that. And that's only starting at low dosage levels. If you assume we then move from a low dosage level to a slightly high dosage level, we're talking about a long lead time in terms of insertion with increasing dosage to try and differentiate signal from noise. Now, why is that important? I think it's important because if you go back, we don't need to put it up, to the graph that Doug had, remember we had that period where solar radiation management could take place, which would buy you time until you deal with the longer-term program of carbon dioxide removal. I'm suggesting that that time period is actually going to move significantly to the right because of the amount of time you need in order to do safety studies in terms of dosage. There's another reason, though, why these two programs do not fit together in quite the neat way that that graph suggests. Think about it from a social and political point of view. Think about what kind of consensus would be required globally in order to implement either of these programs: carbon dioxide removal, sulfur dioxide insertion into the atmosphere. Most people, and I don't have time to go into what's wrong about arguments about moral hazard, most people, I think, would say, of course we should conduct preliminary research and then pilot programs to implement carbon dioxide removal, because what could be wrong with taking out what you've put into the atmosphere? It seems pretty straightforward from a social decision point of view, assuming you can solve the problem of sequestration and get the costs under control. I'll come to that in a minute. But now ask yourself, what kind of consensus would be required in order for the world community to agree to solar radiation management, unless all of the unknowns in terms of unknown risk, particularly at the regional level, were settled? It would have to be a really overwhelming, catastrophic kind of situation. And one of the innovating features about climate change is that it's extremely slow, it's multi-generational, decadal, century-like in its effects, and it doesn't affect the whole of the globe uniformly. Some communities benefit from global warming. So the idea that there would, in the short term, be a consensus that we have to do something displays, I think, a naive view about the way social consensus and social policy takes place. So what is to be done with regard to solar radiation management, with regard to dealing with unknown risks? Yes, we can do important work on the physics of aerosol insertion. We can do important work on the logistics. I think the most important thing we can do with regard to unknown risks is this. We need to develop computer modeling that is powerful enough to deal with predictions of atmospheric behavior to a much more finely leveled degree than we can today. We need to have modeling that can go down to the fine-grained regional level in order to understand what these risks are without actually doing experimentation at scale. And that is a challenge which is plausible, perhaps I'm told over the next 20 years, as the power of our computer modeling with regard to the atmosphere increases. So I've said, I think solar radiation management would be a wonderful thing to do if we had consensus about it, but I don't think we will have consensus about it until we deal with understanding the risks, and I think it's going to be a long time until we understand the risks. Let me talk a little bit in the time remaining about the challenge facing carbon dioxide removal, which seems so straightforward and tempting at the first place. I think there are three areas where carbon dioxide removal faces challenges. If we think about it in terms of air capture using sorbents, physical sorbents, chemical sorbents, we face a problem of physics, which is there's simply a limit to the degree of efficiency that sorbents can display and the amount of energy it takes to recycle those sorbents to use them again. And unless there is some breakthrough in that area, the economics, the scale, and the cost, and the logistics of building enough carbon air capture to remove a significant portion of carbon dioxide from the atmosphere is a significant portion of global GDP. Now, whether or not you think this is an inherent limit based on the physics, or you think some kind of innovation is possible with regard to the physics of sorbents, I'm not qualified to say. I know plenty of physicists who tell me it's a limit of nature, and therefore we will not be able to do it more efficiently than we can now, which is extremely inefficiently. And let me just mention, as a footnote, by the way, that for every 10 parts per million that you remove from the atmosphere of carbon dioxide, 5 parts per million of carbon dioxide will degas from the ocean. So you have to remove a lot more carbon dioxide from the atmosphere if you want to have a net effect of reducing carbon dioxide in the atmosphere. A second option under consideration is to line the ocean, to change the chemical composition of the ocean, reduce its acidity, and thereby increase the carbon dioxide that it uptakes. That seems to me a surprisingly promising alternative to pursue, except that it too involves an enormous logistical commitment. something like mining the total amount of digging mined by the coal industry today, not just the coal, but all of the rock and ancillary material that is mined in order to get the coal out of it. Furthermore, there are complicated effects to do with sudden lining of the ocean on fish fertility, as well as the issue of degassing that has to be approached as well. I think the third alternative that is the most interesting and the most challenging, and philosophically the most challenging as well, is the potential to use current CRISPRs or genetic engineering to change the uptake of carbon dioxide by living matter on Earth, and to do it in a widespread way. This is a seductively interesting option because you get a self-replicating system which will continue once the changes propagate through living organisms to improve carbon dioxide uptake. And there are, in fact, periods in the world's history in which plant life did, in fact, have a much higher rate of carbon dioxide uptake than it did now. But if you think there are problems with genetically modified organisms in the popular mind in terms of food consumption, imagine the kind of dissatisfaction that would have to be overcome in order to implement this at a broad-based level. So I think there are challenges in both areas. The question is, what is the role for aerospace? Well, I'm a philosopher, so I'm a skeptic. So I've been telling you, I think there's a limited role implicitly. There's a role in helping us learn about aerosol insertion in the first place. And I think there's actually a role for you, to the extent that you are modelers, to help with the modeling. But I think it is somewhat fanciful to think that there is a large role in aerospace right now. Let me end, as I did in the beginning, by making a general remark that I make under all circumstances when I talk about climate change and geoengineering, and that is to urge caution against what is known as the precautionary principle. Many people, when they are confronted with the potential of geoengineering, appeal to the notion of the precautionary principle, a principle which says do nothing unless you can be sure that what you do will not make things worse off. Marty implied it in the beginning in his remark of unintended consequences. This is a pernicious principle. It's impossible to engage in scientific research and engineering research without exposing yourself and your community to some risk. If this principle were applied, there would have been no scientific progress whatsoever. The issue is quite different. The issue in scientific inquiry is to take responsibility for understanding and investigating the nature of unknowns. So if, just as I began with the idea that it's implausible to think that we can't follow a judicious policy with regard to avoiding climate change unless we know without certainty that we are causing climate change, so too it's a mistake to think that we can't engage in research unless we can rule out all untoward consequences. The issue is, can we organize a research program that allows us to understand the nature of risk and learn how to limit risk in the process of our investigatory program? Thank you very much.
All right, thank you, Martin. Okay, Tim, you're up.
My name's Tim Langenkamp. I am an energy capital markets lawyer. I live in Houston, Texas. In Houston, Texas, we make energy from oil and gas. And so I grew up doing deals, raising capital for energy companies that were focused on hydrocarbons, whether upstream companies that were focused on finding it and bringing it out of the ground, or pipeline companies that were focused on moving it from the field where it was drilled to the place where it might be consumed or transformed, or downstream refiners and things like that that can turn that stuff into useful products. You might wonder why somebody from my industry is up here addressing climate change. From my perspective, the energy industry is particularly well suited to figuring out how to fund these kinds of activities, these kinds of geoengineering activities. It is easy to think about these projects in the energy infrastructure context, and people in the hydrocarbon industry really know how to do energy infrastructure projects pretty well, even those that are very expensive. Maybe not expensive on the order of nations, but definitely expensive for your average person's pocketbook. It is, again, easy to think about it in terms of energy infrastructure. It's hard to think about it in terms of the other kinds of geoengineering that we're talking about mostly today with solar radiation management. That's a sort of the sine qua non for raising capital is a revenue stream. And it's easy to see how you can generate revenue streams if you're building some energy infrastructure. It's hard to see how you can generate some revenue streams, harder, I found, to imagine how you might generate revenue streams by throwing sulfates up into the air. Or what was it you called it? Not sulfate, something else. Anyway, you throw the stuff up in the air and then you wait for it to come down. In the meantime, you get to enjoy life as not as it was, but at least it's cooler. And then you have to go throw some more up in the air. You could see how you could characterize this as a services play. So instead of building a factory, a refinery, a midstream gas plant or something like that that's going to be there in use for decades, churning out useful products, you could see how you might put together a company that was focused on providing these services to consumers, throwing that stuff up into the air on a repeated basis. The repeated basis sounds good because your customer is going to come back to you as long as you don't muck it up. But a services play is more challenging. It's particularly challenging when lawyers think about all sorts of nightmarish scenarios, and it's easy to see how throwing stuff up into the atmosphere could, by way of those unintended consequences, give rise to some challenging scenarios from an environmental perspective, ones that we can envision now and ones that we cannot. It's as part of the capital raising process, you are supposed to, everybody expects you to, and in fact it serves you under our securities laws to describe the risks associated with investing in that particular business. And so doing that in an environment as little understood as the SRM, the geoengineering, the solar geoengineering environment currently is well, that's particularly challenging. But let's just say that you could get past all of that. Let's say that you could get past the environmental stuff to a sufficient degree, and this piqued your interest enough as a potential entrepreneur to start building a company around this. How would you do that? Well, you'd need some good help to help you think through this process, but much of it is a lot like it's a process that you would undertake if you had invented some new technology or figured out how to improve upon a process, et cetera. You're going to build your company around intellectual property rights. The patent laws in this country aren't terribly long, 20 years for a typical patent. But they are very helpful and they're very robust. It's interesting to think whether something like this, if we were to get past those moments where we are thinking about fearful consequences and to really rush down this road, it's interesting to think whether, given the scope of the climate change problem, and what we understand to be coming our way down those decades. Whether the government who grants that intellectual property right to you might want to curtail your intellectual property rights, your enjoyment of those intellectual property rights, along the lines of what they did with nuclear intellectual property rights back in the day. But eventually that came around for the nuclear power industry, and you currently have the ability to get intellectual property rights, patents in that space. So the intellectual property will be core to building your business in this space should you wish to do so, but it'll also be core, not just your intellectual property rights, but your ability to act in this space is impacted by your competitors' intellectual property rights. And the things that make me concerned about intellectual property rights in this area is the possibility that your competitors may be driven by, with different goals in mind, and not see the world as you do. They may decide to not license their intellectual property to you in order to allow you to provide your service to, I suppose, the governments who are engaging you to throw this stuff up in the air. Or they may be willing to do so, but only at exorbitant royalty rates. So intellectual property can be both a shield and a sword, and you need to be mindful about that. I think one of the ways to guard against that, the danger, as you're thinking about this, assuming again that we can get past all of these issues, and you're trying to build an industry, a business around geoengineering, solar radiation management, one thing that you could do is to protect against others' use of intellectual property through something like a consortium that has the right to grant licenses, compulsory licenses, to people wanting to play in this space in exchange for a reasonable royalty rate. But that way something like that, it's something like what the government did with nuclear patents back in the 40s. The idea is to preserve the public's ability to use this technology. Besides intellectual property, one of the key areas as we think about the other kinds of geoengineering, the direct air capture or the air capture stuff, one of the key areas for potential revenue sources are carbon credits and carbon offset credits and things like that. That it's hard to see how that would really apply for solar radiation management, since you're not really doing anything to address the underlying problem. You're just dealing with the effects of global warming, and only temporarily so. But I suppose it's not impossible that we might find ourselves with some sort of encouragement along these lines. Probably much easier to see a direct encouragement by states and governments actually hiring these companies to perform these services. It's funny, as I think about the solar radiation management, the stuff that we've been talking about today, the injection of sulfates into the upper atmosphere, that stuff looks scary to me from an environmental perspective. It's also so short-lived that it's hard to get my brain around the idea of spending so much money for such a short period of time and then just having to continue it as long as we want to keep the air conditioning on, so to speak. The stuff that is the most crazy, the building of sun shields and the like in orbit, seems much more interesting to me, but for the price tag associated with it, because presumably you would have the ability to turn those things on and off, flip the lever and the shutters open, and flip it the other way and the shutters close and start reflecting the sunlight again, and also probably does much to avoid, I guess, some of the chemical environmental impacts, but not all of the environmental impacts. It's certainly seems to be the case that we don't fully grasp our weather systems and our climate systems, and the idea of reducing the amount of sunlight that hits the planet probably will have some unintended consequences, and perhaps not even short-term unintended consequences. One of the things that you would have heard had my colleague Tracy Hester come to speak to you today. Tracy is an environmental law professor. He comes from my world. He was a partner at a law firm, one of my competitors in Houston. He's an environmental law professor, so he doesn't do what I do, but I often work with environmental law professors on these capital markets deals. So it's always fun to talk to Tracy. Tracy would have talked to you about how solar radiation management might work and might fit into regulatory schemes that we have, whether on the international front under international treaties and frameworks, under customary international law, under, most interestingly to my mind, under state and federal environmental laws and related laws. They're not all environmental laws, but there's some real challenges for thinking, as you're thinking about this as a business, and this activity, or maybe even it's not a business, maybe it's just this activity, whether done by a state or some NGO or something like that, it's easy to see how that actor would find themselves in some hot water in court for that activity. It seems like the perfect kind of thing a law professor would dream up for us to consider in law school. Let's just think about all the ways that this person might be sued under environmental laws, under classic tort laws, negligence, and the like. It's a little frustrating for me. I recognize that that's the case, and I think that's probably a healthy situation because it imposes some cautionary activities as we consider this. But it is frustrating to me because so much of what we've done in our history has had unintended consequences. Certainly, as we think about this very problem of global warming, assuming that it is man-made and that we understand how it's happening, then from the first time that we started burning coal, we started creating this problem. And yet, here's somebody who's trying to mitigate the effects of global warming, and they're running into this nightmarish scenario from a litigation perspective. I mentioned earlier that it's easy for me to think about air capture. Again, you recall what Doug was saying with the two types of geoengineering that we're considering. There's the solar geoengineering or solar radiation management, and then there is this air capture stuff, which is removing the CO2 from the air. It's easy for me to think about that in terms of energy infrastructure, and in fact, I think the most promise in the context of the challenges that Martin described, but it's easy for me to think about how the hydrocarbon industry might find it interesting, a proposal to build a test plant whose goal is to capture CO2 from ambient air And then, well, the hydrocarbon industry is probably going to be most interested in turning that CO2 into fuels that can be used in substitution for the molecules that presumably are going to be increasingly more expensive or harder to take from the ground. But as they turn that CO2 into liquid or gaseous fuels, that's something that will catch some mind share in Houston and in the other hydrocarbon-focused parts of our economy. They won't be fazed by big price tags, even for demonstration plants. Over the last 2 centuries, actually, we have figured out how to, at least certain ways, to finance very pricey technology. Unfortunately, that's the way that is normally done is through a technique called project finance. That's where the bankers line up to diligence the project, and once they are satisfied that they understand how that's going to work, and most importantly, how, once it's built, it's going to tap into a repeatable revenue stream, they will gladly lend money at an attractive interest rate. And that sort of project finance is, again, that's a very time-honored way of building this kind of energy infrastructure. The challenge will be for these test plants. How do we finance those test plants? Again, envisioning an air capture plant here. You will need to work with industry players, the big hydrocarbon industry players, and not just oil companies, but the other players in that space, the service providers, the engineering experts, et cetera. Those are the people that might be interested in investing their effort and their dollars to create a test plant. Again, all with a goal of producing synthetic fuels. You can take CO2 and you can convert it into methane, you can convert it into methanol, you can even get to things like diesel as well. That doesn't do anything to suck CO2 out of the atmosphere, but at least you're not adding to the problem. And if you prove up the technology by that test plant, the technology for sucking the CO2 out of the air, and improve on that technology, you could also envision activities where they stick it in the ground, permanently sequestering that CO2 rather than just creating synthetic fuels out of it. Again, I think the hydrocarbon industry would be interested in and will find themselves actively participating in these kinds of activities. Again, largely focused on building alternative fuel pathways, but that same technology would then be available for use. Again, assuming that the IP is handled correctly, that same technology will be available for use for sequestration purposes, which, done at sufficient scale, could actually make a dent in this global warming problem.
Okay.
Thank you.
Oh, good, thank you. Okay, so Doug is going to get back up and finish up for us.
So thanks. So I think I will hold all of the remaining comments of mine. I'll wind up talking only about the solar radiation management or solar geoengineering part of this, in part because I think it's the more contentious, interesting part, and in part because I think there are plausible roles for aerospace in this area, but it's much harder to see what the plausible roles are for aerospace in the CO2 removal side of things. Planting trees and sucking carbon out of flue gas and storing it underground doesn't sound like aerospace to me. So I think Martin should have done a good job of convincing you that well, Martin and Tim both convincing you that this is a very difficult and risky idea. I would say if the idea of putting megatons of sulfate aerosols into the stratosphere doesn't scare you, I think there's something wrong with you. The problem basically is that this other pathway is also potentially really scary. If you go read the news, there's a giant crack right now that's something like 50 kilometers long in the Larsen C ice shelf in Antarctica. We do not know what the threshold is for losing a lot of the West Antarctic ice sheet, but it is entirely plausible that we have already crossed thresholds that would commit us to 3 to 5 meters of sea level rise from Antarctic ice sheet melt, and we've probably crossed thresholds for sea level rise from Greenland melt. It's just that Greenland tends to melt much more slowly, and so we've got like 1,000 years to get that 7 meters of sea level rise. The last time CO2 was as high as it was going, sea levels were like 100 feet higher than they are right now. In fact, I think the last time the CO2 levels were that high, there were crocodiles living in the Arctic. So this world is potentially really scary. We really don't know exactly what it looks like. We can simply extrapolate and guess from climate models and a little bit from paleo records. But the paleo records are a little hard to interpret because the continents were in different places and things like that. This is also really uncertain. And as Martin said, it's impossible to really do a decent test and understand exactly what that is. So this is fundamentally going to be a risk-risk trade-off. And as we sort of like move along in time, it may well be that it's the risks we want to avoid from unmitigated climate change that scare us more than the risks from geoengineering. So I'll say a little bit about the modeling of geoengineering, what we know, what we don't know, and then wrap up with some of my thoughts on what the plausible roles for aerospace engineers are. So this is a somewhat misleading but optimistic looking chart, if you can see that from the back. This is taking the median over 12 models, and this is basically just scaling the temperature response on the left and the precipitation response on the right from 3 degrees of climate change. And basically the continents warm more than the oceans, so the continents are more like 5 degrees, and the Arctic and the poles warm even more still. That color scale is completely saturated here, and there's some fairly substantial shifts in precipitation as well. If you could somehow manage to constrain yourself to 1.5 degrees of warming purely by cutting carbon emissions and sucking CO2 out of the atmosphere, that's theoretically possible. It's just we don't really know how to practically do that. Then that world is much lower risk than this one. And if you basically take the 3-degree world and you go into a climate model and you simply turn the sun down, so that's saying, for example, if you put sun shield in space and sort of magically turn the sun down, you get a world in the climate models that looks remarkably similar to this one. So it works remarkably well. The temperature, this world is colder than that one at absolutely every grid cell in every single model. That's kind of basic conservation of energy, so that's not a surprise. The precipitation, this precipitation pattern is not the same as that one, but even so, this precipitation pattern looks a lot more similar to this one than it does to the world with 3 degrees of climate change. Looks a lot more similar in most places. So there's one really fundamental misleading observation about this chart, is this is the median over 12 climate models, and the median hides a lot of uncertainty. And so if you had one climate model that said, precipitation in India is going to become disastrous with geoengineering, well, if it's only one model, you don't see that in the median. And so the answer is that, well, as Martin said, there's an awful lot of uncertainty, and some of this uncertainty is really hard to resolve right now. The uncertainty in the response to geoengineering is there. There is also a lot of uncertainty in the response just to CO2 right now. So what do we not know? I'm not going to dwell on all of these. There's sort of things that are at least in principle straightforward to go and measure. I can imagine conducting a field experiment to go measure what the size distribution is of aerosol particles when we start spraying sulfate into the atmosphere, and measure what the impact of those are on the stratospheric heating, stratospheric chemistry, potential impact on seeding of cirrus clouds as these aerosols sediment through the upper troposphere. Then stuff that starts getting a little harder, like this regional precipitation response that's uncertain, that we don't know how you could, well, basically you can't conduct a test, as Martin said. Effects on ecosystems, well, there might be some. It's potentially hard to go measure that as well. The answers to those depend on how much you do. How well can we design the system given the fact that it's uncertain and nonlinear? What are even the limits to how well we can know the system? And then probably the hardest questions of all, I gave you this nice naive chart back here saying, well, posing it as if it was a decision between following this path and following that path. But it is pretty likely, I think, that if you were to start doing some amount of solar geoengineering, or even to like talk about it seriously, maybe people would say, oh great, we don't have to cut our carbon emissions as much, and they'd actually emit more CO2. And you can also be willing to bet that, you know, if region X experienced a drought a year after you started geoengineering, it doesn't matter what the climate models say, whether that's connected to geoengineering or not, people are going to go blame it on the deployment. And so these questions here become really, really hard. And the bottom line is, I don't know. I certainly don't know how to answer these questions. I don't know that anybody really knows how to answer those questions today. So this is going to take a lot of research. This is not near term. If you wanted to go fly airplanes up into the stratosphere and dump crap up there, it's not fundamentally hard to do. You could probably start doing that in a few years and cool the planet. But if you wanted to do it intelligently, that's probably at least decades away. I'm just going to walk through 4 areas where there may be a role for aerospace. This first one is essentially the stuff that I do. So I'm a controls engineer by training, so optimization, feedback, and so forth. That's the original thing that got me into thinking about climate science, was how do I apply those tools in climate science. But there are a couple of broad questions. So if you look at this map here, this one's just, whoops, press the wrong button. This is turning the sun down. Well, really what we wind up doing most likely is putting aerosols into the stratosphere. But you get to, if you don't like this climate, if you basically say, my model predicts there's going to be some precipitation change in some region that I don't like, maybe by putting the aerosols in at a different latitude, you can do a better job. So that's one of the things that I'm involved with right now, is how do you actually go design this, treat it as a design problem.
What is the approximate time frame that the aerosols remain in the atmosphere?
In the stratosphere, the lifetime is of order a year, ballpark. So the advantage of putting it up in the stratosphere is stratified. It's heated from above, so it's stably stratified, so the lifetime is much higher above the tropopause. If you put stuff in the troposphere, it's heated from the troposphere is heated from the bottom, so it's convectively unstable. So you put stuff in, it properly rains out. So that's actually an entirely relevant comment, and also in terms of how much you have to put in. The reason for putting it into the stratosphere is you get a long lifetime. So the amount that you have to put in is relatively small compared to what we currently dump into the lower atmosphere. The second thing that I work on is the question about, well, okay, there's a lot of uncertainty. Can we design strategies that still achieve goals despite uncertainty? This plot that's a little hard to read here, this came out of a model simulation this summer, putting aerosols into the stratosphere in a climate model. With all of the uncertainty and nonlinearity, wrapped a feedback loop around that. So we were adjusting how much injection to do every single year in order to maintain a constant temperature, and that feedback loop was stable. So, plausibly there are some strategies that might help us with managing uncertainty. There's lots of issues there. The real reason that I want to mention this type of stuff is a lot of the research that's been done to date in geoengineering has been fundamentally curiosity-driven research by climate scientists. So I've got a climate model. It's really easy to take the knob that says here's the solar constant and just change it. If I've been used to simulating volcanoes, well, I can, instead of putting in a volcano once and looking at the response, I could just say, all right, I'm going to inject SO2 every year for a decade and see what happens. That has told us an awful lot about the response of climate models, but fundamentally, if you really wanted to get to a point where you could make an informed decision about geoengineering, you'd need some sort of a strategic mission-driven research, and that's the sort of thing that engineers in general are much more trained to do than climate science. So I would actually say somewhere along the line, and I personally would think sooner rather than later, because I think it'll actually take some time, we really need to ramp up our research funding in geoengineering from the current level of, well, within a rounding error, 0. When you think about an aerospace role, having talked about stratospheric aerosols for the last hour or so, most likely the first thing that one thinks about is deployment question. My personal guess is that these decisions are at least 20 years in the future. It is entirely plausible that some catastrophic climate event will occur, you know, some massive ice shelf will collapse in Antarctica 5 years from now, and somebody will go, we're suddenly committed to 3 meters of sea level rise if we don't do something. My gosh, we have to go do something right now. So it's plausible that somebody might try to do something faster than that, but my guess is probably not. My personal guess, somebody might disagree with me, is that developing the deployment capabilities are relatively easy compared to all of the really hard problems about how do you govern this and how do you predict the climate consequences. It might not be quite so easy because the modeling results that we did this summer are suggesting that we actually want to inject this a little higher than we were previously thinking. This is another hard to see plot from the back of the room, but that's the tropopause right there. So in principle, everything above that is the stratosphere, but the circulation in the stratosphere, there's a shallow branch of the Brewer-Dobson circulation where you put stuff in, it doesn't last quite as long. You'd really rather put it up a little bit higher, closer to 25 kilometers, and that's starting to get a little harder to get to. In terms of how much stuff you need to put in there, from our model runs this summer, we were getting about 1/10 of a kilogram per teragram of sulfur dioxide. So if you want 1.5 degrees of cooling, you're talking about injecting about 15 teragrams of material up to 25 kilometers. So you can tell me how hard that is. Aurora Flight Sciences did a study a few years ago. I don't know that they used quite these same parameters, but they basically concluded that the cheapest way to do this was to launch in airplanes. They looked at balloons and rockets and all sorts of other things. And basically, you know, take a Gulf Stream, put low bypass ratio engines on it or something like that. If you want more details, you can go look at that paper, and it'll tell you all of their analysis. The other comment in here is, although it is useful to know things like how much more expensive is it to get up to 25 kilometers, at some level it probably doesn't matter, because the real issues here are all of the bigger risks to the climate system. And in terms of the costs are probably not so much how do you get the sulfate up there, but all the observations that you'd need to conduct, and potentially compensation for people who experienced a drought and wanted to blame it on the geoengineering. The third area, this is not my specialty, so I'm not going to say very much about it, is the role of observations. If we ever were to deploy this, we clearly need to be monitoring probably a lot more things than we're currently monitoring about the planet in order to understand exactly what's going on. And simply understanding the risks of deployment, we probably need some small-scale field experiments. And so there's some potential role for innovative test beds of how do I go up into the stratosphere cheaply so that it doesn't cost $10 million to go conduct a balloon experiment and measure aerosol microphysical growth assumptions. You know, how do I go up into cirrus clouds and measure properties in cirrus clouds today so that I can get some idea of how aerosols might affect them? Those experiments today are probably $5 to $10 million type experiments. And then the last thing that I'll talk about, and then try to make sure we've got lots of time for questions, is the potential for space-based. So I spent most of my time talking about stratospheric aerosols because that's the one thing I know will work and is relatively cheap. The marine cloud brightening I mentioned early on, I actually don't know for sure that it works. It requires experiments. Doing something in space would definitely work. It's just expensive. So one of the ideas that's been floated is rather than going to Earth orbit, put a cloud of reflectors at L1, the stable Lagrange point between the Earth and the Sun. And if you want to block 1% of sunlight, so that's about 1.5 degrees of cooling, you can simply work out the projected area, that's pi r squared. If you're thinking Earth orbit, you just got to multiply all these numbers by 4. If you take that area and you said, well, we want to be able to provide that, say, in a 50-year time scale, you need to build 70 square kilometers every single day, day in, day out for the next 50 years. You can probably do something thinner than this, but if you just take the James Webb one layer of the James Webb sunshade, that's 25 micron kapton. Go look up the density. That gives you a mass 4 times 10 to the 10 kilograms. Go look up the Delta IV payload, and that gives you 270 launches every single day for the next 50 years. And that's
There's
the
some
point.
people in the room that probably think that's a great idea.
Well, there's some people in the room who might make a lot of money, but at that point, you then start to have to worry about the carbon emissions from all of the rocket launches that you're doing. And you then need to ramp this number up in order to compensate for all of the warming from the carbon launches. So the short answer from all of that is it's kind of fun and entertaining to talk about space-based stuff, but without a fundamentally new idea, it's not going to happen. So fundamentally new ideas are things like how do we go manufacture stuff in space with material that's in space already? So capture an asteroid, use the asteroid to build your whatever you're using to reflect sunlight at L1. The best analysis that's been done to date was one by Roger Angel. This was in Proceedings of the National Academy back in 2006. And he basically more or less, he did more or less analysis kind of like this, although I think he basically was assuming 1 micron thick. I just started with the James Webb number. So I think I will stop there and take more time for questions. In terms of these sorts of numbers, given that the whole reason for thinking about geoengineering is that we don't know how to slow down our energy infrastructure fast enough to avoid really, really serious risks to our climate change, solutions that are in the, I don't know what's past $1 trillion, quadrillions of dollars, it'd be cheaper to just revamp our energy system in the first place, and it's probably cheaper to just go suck the CO2 out of the atmosphere and store it underground. Okay, so I would say, there we are. So it's certainly plausible that solar geoengineering could reduce the aggregate climate risks. We certainly don't know that today. I think whether or not it's a good idea, I think it is certainly plausible that some level of solar geoengineering will be deployed. It's cheap enough that somebody might decide it's a good idea. Stratospheric aerosols are probably feasible in some gross sense, but not likely in the near term. And there are my sort of 4 broad areas that I can think of as potential roles for aerospace. So I'll stop now and we can all take questions.
Clarification. Can you just go back to research number 1? I just want to clarify your comments about uncertainty have to do with experiments to determine uncertainty, aerosol insertion, not the generalized issue of uncertainty of regional behavior that we were talking about.
Yeah, this is actually, that's a good point. This is, there are some things you can do that will help with certain types of uncertainty, but not broad uncertainty.
Okay, great.
So if your uncertainty is simply, I don't know how much cooling, how much sulfate I need to inject to get a certain amount of cooling, that's easy to compensate for.
Agreed.
If your uncertainty is, I don't know whether the precipitation over the Indian subcontinent is going to collapse,
Right.
well, really the only way to find out is to either have a very good climate model that you trust, and it's hard to figure out how to trust it, or to try it and see what happens. Which has
You might be able to trust it by telling you other things that confirm the general properties of the model that are less risky things to throw into question.
Right, like monitoring the next volcanic large volcanic eruption, because we don't really have enough data from Pinatubo to to fully validate our models. So.
Okay, thank you, Doug.
Okay.
All right, so we do have several questions that have come in.
Where are they coming from?
They're coming out
Out of the ether,
of the ether, the internet.
from the stratosphere.
No, many people have apps on their
Okay,
phones and
just
computers, and
wondering.
they're sending.
right.
We can also respond to questions from the audience if you come forward and state your question. But we have a few here that we're gonna work on. One of the questions, and then also the members of the audience get to vote on their favorite question. So once somebody puts a question in, other audience members can vote that up the chain. But as the moderator, I can also skip questions, concentrate on different ones. Okay, so the first question has to do with, can we strategically geoengineer and perhaps commercialize the environment to benefit specific region? So you talked about there could be regions where you have droughts. Could you do it in a way that would put more water in those places, heat up the cold places, et cetera?
I would say maybe a little bit, but you certainly can't tailor the entire climate system just because of the energy transports within the climate system. And with stratospheric aerosols, they distribute longitudinally very quickly, and they tend to distribute hemispherically as well. So you can certainly say, I'm going to put aerosols in this, more aerosols in this hemisphere versus that hemisphere, and you can do that to some advantage. If you cool one hemisphere more than the other, you shift some of the tropical precipitation around. So there's a little bit of freedom to play. There's certainly some freedom to improve how well you compensate, but you certainly cannot weaponize this in the sense that you can't say, oh, I want to make that country's climate really terrible without making your own climate really bad as well.
Right, so it's a lot more complicated than a cloud seeding type discussion where you get rain and your neighboring country doesn't.
Yeah.
But
So-
it's a lot more complicated.
So
than that.
there have been some ideas floated for more regional scale things. If marine cloud brightening worked, you could do it at a much more regional scale. And there's ideas for also like taking deep ocean water and pumping it up to the surface to cool ocean surface in a very local region. Those things actually scare me a lot more than the global stratospheric aerosols because of the potential to say, all right, well, okay, that helps my rainfall here, but that meant somebody else didn't get rainfall.
Okay. Let's see, I have a question also. Has anyone looked at studying the atmospheric chemicals, the environment, after a large rocket launch? Say a space launch, there's a lot of chemistry going on in the atmosphere. Sometimes there's a plume going up. Any research in that area that you could use to calibrate your models for the atmosphere? When you mentioned volcanoes could be used.
That is a good question. I'm not aware of any. My guess is that most of the things that are going in are so different, that the environment is so different that you're not going to get the same chemistry. There's a few issues with doing, so the aerosol microgrowth, the SO2 oxidizes to H2SO4, that takes a period of several weeks and then coagulates into small droplets, or nucleates into small droplets that then coagulate together, and eventually enough material gets glommed onto these aerosols. Eventually they might fall out. That period takes weeks to months. And in the meantime, so at high latitudes, one of the particular issues in chemistry is ozone photochemistry. So any surface provides, the chlorine mitigated ozone hole is due to chemistry, surface chemistry. So there has to be a surface. So as soon as you put more aerosols into the stratosphere, as long as we've still got fluorocarbons from the 1970s and 1980s, which will be true for another 20 or 30 years, you get more ozone loss. So it's validating all of those types of reactions, and I don't think those are the same things that you get from.
Can I follow that up? Do you have any updated studies on the acid rain consequences of concentrations necessary to produce the desired cooling effect and what that would do to carbon dioxide uptake by trees?
Macroscopically small. in that the amount that you need to put into the stratosphere is of order a few percent of what we put into the troposphere. So in terms of CO2 uptake, actually, this is probably one of the cheapest ways to suck carbon out of the atmosphere, because if you cool the planet but you still have elevated CO2 levels, you probably enhance the biosphere uptake of carbon and the ocean uptake of carbon.
Okay, another question. What other side effects of the sunshades have been studied? And the person listed vitamin D that humans might like. I was also thinking incidence of skin cancer, maybe that changes. And then how would it affect plant growth? You could get a feedback on the plant growth that you might not like. It might be detrimental to the whole CO2.
Is this for solar shades or for SRM?
Well, it says
Shades.
it says sunshades.
Yeah.
I don't know, how would it apply to either?
So broadly speaking, to cool a planet by like 1.5 degrees, you have to reflect about 1% of the sunlight. So if you do that with sunshades in orbit or at L1, you're just reflecting 1% of the direct light. It's not a big deal. If you're doing that with stratospheric aerosols, sulfate is a terrible backscatterer. So to reflect 1% of the light, you're actually scattering about 10% of the light. UV goes up because of the ozone reactions that I mentioned. So skin cancer goes up. The backscattering basically means the diffuse light goes up and the direct light goes down by more like 10%. And that change in the ratio of diffuse to direct light might have all sorts of consequences. In terms of plant growth, it, as I said, is probably beneficial for plant growth simply because of the CO2. You still have the CO2 fertilization effect, but you no longer have as much heat stress. But those are all,
But just to be clear, the plant growth doesn't help you to the extent those plants decay and release the carbon dioxide back into the atmosphere.
They're not permanent.
So it's a pretty zero-sum game in that regard.
And I think all of the ecosystem response stuff is broadly fairly uncertain.
Okay. Let's see, we have a suggestion to use solar-powered robotic aircraft that autonomously plant trees or drop seeds. That seems like a good idea with very little negative consequence.
Well, again, the problem of planting trees, aside from their inefficiency, is, as someone else said, unless trees drop diamonds instead of leaves at the end of their cycle, they give back most of the carbon dioxide they've taken up. They don't during the period they're growing, but they only grow for a limited amount of time if they're fast-growing trees. So then you're faced with the problem of what you do with the tree trunks. Unless you do something, they too will decay and release carbon dioxide into the atmosphere. I suppose you could bury them all, but then you've got a massive burial project involved.
So an argument that increased plant growth is going to somehow mitigate the CO2 in the atmosphere, that is, you don't have a lot of confidence in that?
Only if it's associated with carbon dioxide capture from those plants and sequestration of the carbon dioxide capture. Now, if it's a closed energy system, then you can use that efficiently to stop putting more carbon dioxide. But the focus of this discussion here is basically a negative emission strategy. And plants won't work for that unless you have it associated with a carbon dioxide capture and sequestration program.
So just two more comments on that. So it is true that a mature forest stores more carbon than agricultural land.
For sure.
But if you were to reforest every single acre that has ever been cut down since the Industrial Revolution, you would get something like 1/3 of our current atmospheric CO2 just from that. But of course, we're using that land for other stuff.
Right.
So yeah, basically, as Martin said, you pretty much have to burn it in a power plant and then go store the carbon for it to really matter. And you have to do that on a truly massive scale.
Or associated with something where you are concentrating carbon dioxide and sequestering it.
Yeah, just because it's not the panacea doesn't mean it shouldn't be looked at.
That's true.
I mean, there are a bunch of little projects that could contribute to this.
Well, certainly reducing CO2 emissions is done by a small project at a time, a small piece at a time, and it adds together into something significant.
Yeah. So that's a good point.
Yeah. Okay, so a question about One of the things scaling up our energy use is population growth. Is there other ways of reducing the population growth faster than just the economic discussion that we had?
Well, did you? Sorry. Well, yes, you could stop treating AIDS, you could stop treating malaria, you could hope for many kinds of pandemics which reduce the population, but that's considered generally unacceptable. The interesting thing about fertility studies is that people think that contraception is a key, or modern contraception is a key. Interestingly, in the 19th century, people were implementing modes of contraception effectively long before there were modern contraception was available. And more distressingly, we have studies today that show that the mere availability of contraception without prospects for economic growth does not lead to reduced fertility at a significant level. The most important variable in terms of reducing fertility is that, at least in traditional families, female members of the family unit are earning enough income so the opportunity cost of having more children goes up relative to the income that they forego by having more children. That implies that you need economic growth in order to provide those economic incentives which produce declining fertility.
So you didn't think you were going to get any discussion of that topic at SciTech, did you?
I didn't.
Okay.
You could, of course, while we're at it, add contraceptives to the water along with the fluoride.
Great.
We never said we were avoiding controversial topics today. Okay, let's see. Do you believe it will take a catastrophic event to spur action to climate control, or will it be too late at the point that occurs?
I think that's an interesting question because Doug made a hopeful comment, which he said, well, maybe an ice shelf will collapse in 5 years, and then people will react to that as a crisis. I have the opposite intuition. The ice sheet will collapse, but because the effects of the collapsing ice shield won't take place for a long time, I don't think people will react that it's a crisis. And the question is, how far off are we from crises that will materially affect people's quality of life? Let me just say there's a paradox here, because in the case of the first world, the long-term effects involve receding, moving away from Florida, moving away from Louisiana, rebuilding cities further inland. These are not insurmountable challenges for very advanced economies. The significant challenges for poorer parts of the world are going to materially affect people who live at a subsistence level. And the world is not great at reacting to the worsening lot of those people. The effect on species may be extinction of up to 80% of species, but the world has not reacted with alacrity to extinction of species. So when people talk about a crisis that will prompt action, I'm actually skeptical about exactly what that crisis would be that would bring about global consensus. I think something else is happening. If you look at the graph that Doug had from the beginning, that red line, until Paris, that red line reached 900 ppm by the end of this century. That is, if you extrapolate it from the current growth of energy, we reach 900 ppm. Now, Hansen has argued that once you reach 900 ppm, you actually go above a zero probability of the oceans boiling away over tens of thousands of years. You end up with possibly extinction. But it's extinction far enough away that I don't think even that would have an effect on people. So I think the idea that a crisis will affect us is, in a sense, an illusion that we need to shake ourselves off in terms of the requirements for action to take place. I think the other thing, let me just get this off my chest, I think the other more important illusion that we have to work to remove, and I think it's been propagated largely by people like Al Gore, who's wonderful in other respects, which is if we only try hard enough, we can turn around the energy system in 20 years and have a fully renewable system. Posing that as a third alternative, namely the status quo with some slow adjustment over 50 years in terms of the energy portfolio, or the kinds of things that we're talking about, outlandish as they may be, offers the illusion that there is a third alternative. And I think that is a deeply misleading characterization of the nature of the energy system and its infrastructure and our ability to turn it around. Sorry, I didn't mean to lecture.
Second that. I would say if you think we're going to avoid dangerous climate change simply by cutting emissions and moving to renewable energies, that's a pipe dream.
Well, it just ignores the stuff that we've already put in the atmosphere.
I'm not sure if that's the case. I'm not sure if we could wave a wand and stop tomorrow. I think that those consequences are quite manageable. The problem is rather to do with prospective energy demand and the impossibility of satisfying that with a clean energy portfolio on a timetable necessary, and the impossibility of cutting it back.
Okay, I have an interesting political question that's come up and been voted up the line here. So let me read it and then let's comment. As people who have spent much time studying this issue, why do you think conservatives in the U.S. are certain it is not a problem?
Well, I think there's a misleading premise here. I don't think it's certain. I don't think conservatives in this country are certain it's a problem. I have it on the authority of some unreliable source on the internet, I'm not sure which, that 85% of members of Congress know climate change is a serious problem, but they're covering their political rear ends by pretending it's not a problem in order to keep their constituents happy. If we're talking about the population in general, we have polls that show a vast majority of people in this country think that climate change is a problem and it needs to be dealt with. But to the extent there are some conservatives who believe in it, I don't know the amount, and some conservatives who sincerely believe it, I think the problem is that we have miseducated people into believing that certainty is a requirement for proceeding with some scientific program. So, to the extent that someone can make a serious argument, we can't be certain that Darwin is correct, and therefore it's possible that creationism is correct, and therefore there are two sides to this debate. We foster this idea that there are two sides. If there are two sides to every debate, then they deserve equal consideration and they deserve equal weighting. And so part of the problem is a level of scientific illiteracy that we have bred in this country that gives rise to this kind of discourse.
I think the only thing I would add to that is the word money. The one place that clearly stands to lose from aggressive emissions reduction is the fossil fuel industry. The fossil fuel industry has very deep pockets.
But at the same time, Exxon itself, I can't speak of whoever just resigned to become Secretary of State, but Exxon and most of the fossil fuel companies have actually been agitating for the Paris Agreement to be implemented and from Trump not to renounce it, because what's more important to them is a long-run horizon of certainty in which they can begin to deploy their research priorities in other kinds of areas. So I'm not sure how, it may be true of the coal industry, but I'm not sure how craven the position of the major fossil fuel companies is in this regard. I don't know if you, as a financier, have run into that.
I think that it is easy to continue to look at the world as you've looked at it, as your family before you in the family business looked at it, and it is hard to imagine deviating from that path, which provides your family with a nice income, when you're hearing competing storylines that have all sorts of flash around them, and that suggest that there is a debate on anthropogenic climate change. I think that's a hard thing to do, and so I'm thinking about the average person. I think that's a lot of what's going on, and some of that's money, some of that's a way of life. I think it's especially if you look at the political stances of members of Congress and members of the various presidential campaigns in recent years. There's this wonderful YouTube video that shows, yes, it's a problem, it's a man-made problem, it's a problem, and I'm sitting here today with Nancy Pelosi, it's a problem. Hey, it's not clear that this is a problem. It's not clear at all that this is the cause here. We need more science, we need better science, we need to understand this before we consider acting. It's a pretty marked shift from the same people.
Yeah. We're not sure if conservation of energy still holds.
In relative terms, what are the energy costs associated with CO2 absorption or SO2 ejection as a fraction of the current energy consumption? Or maybe what would a target value be that would make it feasible? I don't know. So what percentage could we pay to build a CO2 absorption system on top of our energy costs of today?
Could is a vague question in this area. I mean, it seems to me the standard by which to examine this question is what is the social cost of fossil fuel right now that we don't incorporate within it, and what would coal cost if we incorporated it in it? And I don't know if you guys have a cost figure in mind. I mean, let's say $30 a ton to $80 a ton. Could we do carbon capture at $30 to $80 a ton? Well, if Klaus Lackner is to be believed, yes. If the associations that examined his proposals are to be believed, absolutely not. It's hundreds of dollars a ton, and that's before you deal with the question of the cost of sequestration of carbon dioxide, and that's before you deal with the level of degassing from the ocean, which requires you to extract more. So as far as carbon dioxide is concerned, I would say current thinking is hundreds and hundreds of dollars, and a significant portion in the end of global GDP if you want to have a significant impact of concentration of parts per million of carbon dioxide in the atmosphere. I mean, if you think about a program, let's say, to reduce by 50 ppm every 20 years, with current technology and current science, unless there is a change in the physics of sorbents, it's gigantic. In terms of sulfur dioxide, it's a fraction of that, and it's even if you repeat it on an annual basis, but that only buys you time, as Doug has said. Yeah.
What we can be pretty sure, though, that current technology and current pricing won't remain in the future. We won't be saddled with this in the future.
I don't see how you can say that from the point of view of the physics of sorbents, unless you I mean, that sounds like a...
If we look at other industries, the technology has gotten better and the technology has gotten cheaper. I'm not a scientist. Don't ask me about the physics of sorbents, but
we're currently putting 40 gigatons of CO2 a year into the atmosphere, and so to pull that out, 40 gigatons of CO2 per year out of the atmosphere is a really huge number. I mean, it's certainly a lot more than our entire fossil fuel industry, because CO2 weighs more than carbon, the hydrocarbon. And it's a gas, so it's harder to work with.
I nonetheless think that we will see people in the near future move towards air capture test pilot projects, and those projects will get funded.
So there is one.
Right, and we will see with different technologies, we will see these things start to come out into the wild.
David Keith at one point said that if the price of carbon was $100 a ton, he would be very rich, and he's backed off from that now that they've actually tried to build a pilot plant. But whether it's $100 a ton or $200 a ton, if you put a $100 a ton price on carbon today, that would really, really accelerate the renewable energy, because that would certainly shut down coal permanently.
Well, there are 3 pilot projects. Their economic feasibility depends on catering to the fossil fuel industry by providing concentrated CO2 streams for injection as part of oil production. But again, I, with all due respect, I don't think that the line you're taking is a credible line to say, well, I'm sure there will be an innovation in the future. We're dealing with some pretty fixed properties of chemistry to do with sorbent uptake, the energy requirements to recycle that sorbent, whether you use fossil fuels or renewable fuels to do that. And I don't see any reason to be simply optimistic that there will be innovation in that regard. I mean, maybe there will be, but I don't think one can bank on it in that regard. I think the much simpler issue is what Doug said. If we put a high enough price on, if we put a high enough price on fossil fuel, the problem would solve itself by the logic of the market.
Well, and that's another thing, though. I mean, one, we should ask Klaus to come and participate in these conversations so he can perhaps provide an answer for you. I'm certainly not qualified to provide an answer on the physics of sorbents. But the other thing is that you could see these in the wild well before they're economic. And so whether they are funded by governments or they are funded by nonprofits, you might see these despite them not being economic.
Yeah. To give the audience a reference, if you had a $100 a ton price on CO2, what would that do to the price of a barrel of oil or a gallon of jet fuel or gasoline? Is that?
No, I was talking about a $100 supplement. Well, maybe you.
Yeah, the answer is I don't remember. I think $100 a ton is not. I think it's a couple of dollars on the price of gas. I don't actually think it's that huge a number. But,
well, a lot of people would think that was a pretty huge number.
Well, but I mean, what's gas
Here.
now is $2 a gallon.
Yeah.
It was $4 a gallon not that many years ago, and it didn't destroy the economy.
Mm-hmm.
Okay.
That seems about right, yeah. Okay, let's see. Oh, we have a deplorable skeptic in the audience. And they say, suppose renewable or nuclear energy were used to heat large amounts of water and then immediately pumped deep into the ocean. Since it would be well below the surface, wouldn't radiation to space stay the same? Wouldn't ocean temperatures increase over time? Are you 100% sure something analogous to this is not already happening, rather than atmospheric physics being to blame? Do you understand that?
I'm not sure I understand the entire question, but relative to the basic physics of climate change, it's like, I would say, fossil fuels contain carbon, they release CO2. When you burn them, CO2 absorbs infrared, which is really easy to measure. You can measure the CO2 increase in concentration in the atmosphere. The Earth emits in the infrared by black body radiation, and then you get sigma T to the fourth, so you can work out a climate sensitivity, and conservation of energy. And so unless one of those things is wrong, burning this amount of fossil fuels should be heating the planet. And so to say the planet is warming and maybe it's not CO2, you have to both say something in our fundamental physics is wrong that would say it is warming, or something in our fundamental physical understanding is wrong that it's not warming because of the CO2, and come up with a fundamentally new mechanism that nobody's ever thought of in the last century for why the planet is warming exactly the way it is. So I would put the probability that this is not due to human emissions of carbon at 0. I would say it's about the same probability of whether the Earth is round or not. Martin might disagree with me on the level of certainty of that, but
I would think so.
Well, yeah, nothing is certain as far as
well, at some level, yes, you're right. Absolutely nothing is certain. I mean, I could blindfold myself and drive home, and I might make it home alive. You can't prove that I won't. So in that sense, anything about the future is uncertain. So it's certainly possible, for example, that there's some nonlinearity in cloud feedback that will cap warming at the current levels, and we will never actually get any warmer no matter how much we burn because of a nonlinearity we haven't discovered yet. But there's certainly no evidence from the paleo record that such a thing exists. The specifics of the question I didn't quite follow.
Yeah, it had to do with pumping heated water into the lower portions of the ocean, and then it would take time to heat up. I don't know.
That is actually a plausible geoengineering scheme would be take surface ocean water, pump it down, and deep ocean water up. And then now you have cooler water at the surface, and that cooler water cools the atmosphere.
And then it would take time for that temperature to equalize, and that would give...
I mean, eventually what happens is, right now we're just warming the surface layer of the ocean, but eventually that thermal perturbation does go all the way down to the deep ocean over thousands of years.
Thousands of years, a very long time scale.
Yeah.
But if you pump water from deep water, that has carbon dioxide held under pressure. As it comes to the surface, it will begin to release it. So
Yep.
you have a cost in terms of
Yeah.
increased release.
Also has impacts on cloud cover, so radiative feedbacks that are less obvious.
Okay, a comment here is, can aerospace technologies somehow do a better job in driving humans to a more carbon-light lifestyle in a significant way? And should we focus on that? It sounds like efficiencies to reduce our amount of carbon emissions. And though certainly we know how to do that, and we've heard a lot of difficulties and skepticism and risk involved in some of these more exotic things that we mentioned. Is that the conclusion the audience should come away with today? That we should do some research on the more risky things, but we should really double our efforts to work on the emissions reduction?
I think when I've talked to random people in the public about this, usually the reaction I get is, wow, if serious people are so terrified that they're willing to consider crazy stuff like that, maybe we should take Plan A more seriously. Yeah, I would say aviation is actually one of the sectors that's really hard to get the carbon out of. And so to the extent that one can reduce the CO2 of aviation, that would actually be a pretty big deal. Don't go proposing personal flying cars.
A comment. So is there any reason to be optimistic in a 50-year scenario? So
Optimistic about what?
I don't know.
I'd say,
Our lives. The lives of our children, maybe.
so that first chart that I put up, I would say that there is certainly a way that you can look at that chart and say,
Can we bring Doug's charts back up?
here's a,
Or is, I don't see. Okay, just go ahead.
there's certainly a way you can look at that chart and say, here's a hopeful way that there is at least a pathway that we're not committing future generations indefinitely to a fundamentally different planet than the one we're on. So the long term, you do CO2 removal, and in the short term, you do a little bit of solar reduction to avoid the catastrophic consequences in the short term. So I could look at that picture and present it as an optimist, saying, great, the alternatives are dire. I don't have I left the clicker over here. But,
Oh, yeah, there you go. Yeah, there was also a question on that graph. On the role of geoengineering graphs, shouldn't the top line be an upward exponential, not a steady state straight line?
Probably.
I don't know why.
Whoops, wrong one again. The shape of that's pretty arbitrary. I didn't put any units on this on purpose. Eventually, this will tail out just because we'll run out of fossil fuels, but that point is pretty far up the curve. And it may be that even without any emission policies, carbon pricing, or anything whatsoever, that this will tail off simply because other forms of energy will become cheaper. The old thing about the Stone Age not ending because we ran out of stones. So it is quite plausible this will level off somewhere. It's just very unclear where it will level off. And at that point, you've got all of the carbon stored in the permafrost that's also going to get released. Potentially some of the deep sea carbon as well being released.
Okay. We have, let's see, another question related back to economic growth and population growth regarding that link. What about societal differences? In places like India or the Mideast, I'm not sure the economic growth will lead to increase in female workforce and hence reduction in fertility rates as it would in Western societies. Any comments in that area on societal differences in that correlation?
I think there's a misperception about the rate of female employment in India. The problem in subsistence economy is the whole household has to work. It has less to do with people not working than the kind of work that they do. In subsistence societies or low technology agricultural societies, or societies where people work at home, you can both have children and engage in economic productivity as a woman. The issue is, and this happened in the Industrial Revolution in Europe, when women begin to work outside the house, then the compatibility of having children and working begin to rub up against each other.
So in some of the societies, are women permitted to work outside of the home?
Well, there are some societies where women are not permitted to work out of the home, and those societies are impervious to that. There are some societies, like my own society, a Jewish society, where there are religious elements in the society, believe there's a commandment for God to have many, many children, and they're impervious to this as well. So there are certain societies where it's not going to work, but in most societies, it's a pretty stable relationship.
Okay, we're almost out of time here, but let me ask a question that's been up for a while. Solar radiation management won't mitigate ocean acidification.
Correct.
How is the risk of that viewed relative to the risk of warming?
So just to clarify that, if you drew this as a straight line and you said this was global mean temperature and that's a straight line, not every other variable on the planet is going to be a straight line. So ocean acidification will be mostly unchanged whether you do the solar geoengineering or not. It actually might get very slightly worse because a colder ocean absorbs more CO2. So I would say that's yet another reason why this is a horrible idea, because this doesn't do any. So in this case, the ocean acidification would still be more or less following that chart. This is clearly not a panacea. It doesn't solve everything. It potentially solves some things. I think in terms of, say, coral reef health, they're affected both by temperature and ocean acidification. So it is probably still true that ocean ecosystems are likely better off on that pathway than that pathway. But
let me just say, if you engage in CO2 removal by liming the oceans, then you're dealing with two issues at the same time. And I think that's a major argument in favor of significant research into ocean alkalization as a mode of CO2 removal. Some of the most interesting research going on has to do with examining intervention, not to do CO2 removal from the atmosphere, but to reduce the amount of ocean degassing that takes place. Ocean degassing vastly outpaces the amount of human CO2 introduction into the atmosphere, and it's actually concentrated in certain areas of ocean upwelling, where there's intense ocean upwelling of cold, low ocean holding CO2 under pressure. And so the idea is that if you intervened in those areas and limed those areas significantly, you could actually have an effect which would counteract anthropogenic CO2 output and more, resulting in net negative emissions. Downside is that these areas of ocean upwelling are major areas of fish nutrition. And so you pay an enormous price in terms of extinction of certain species and disruption of the food system for large numbers of people. So, as with everything else, there is no free lunch in this area.
And there's less free lunch in this area than most. Very good, thank you. We are out of time. I'd like to thank the panel.